Hello everyone, this is Energy Crafts. Today I'm going to talk about the iMax B6AC and some problems that I had and the solutions I came up with. This video should be useful for anybody that's considering buying one of these knockoff discharger units, or if you already own one and yours is acting crazy and erratic and having inconsistent capacity measurements, especially for the lithium-ion battery cells like what I'm using. Please stay tuned. I'm going to explain everything, but let me just, by the way I explain it is to tell my story of what I encountered, because it may be useful to what you've encountered as well. So the first thing is here's the box. A knockoff iMax comes in, and the iMax, as everyone knows, already comes with these different connections and adapters and so forth. And at first glance they look pretty good, but the truth is the wiring is pretty thin gauge, so you have to watch out for that. When you're doing any kind of testing, you need to make sure that the gauge of the wire is adequate for what you're doing. So now let me show you the unit that I've been using and that had some problems. So this is the knockoff unit. It has the gold dual power colored emblem. And I'll show you, well, first I'll say this. When I bought this, it was wintertime, and I was using it for like 6 months, and I didn't encounter any problems that I knew of. And then as summer came along, I was sitting on the couch and I was doing some charging and discharging to check laptop cells in order to build a power wall. And I was smelling this plastic smell in the house, and I was wondering, where is that smell coming from? And then I finally realized that it was coming from the iMax while I was doing a charging or discharging, I forget which. But anyway, let me show you what I encountered. So I've already taken the screws out of the side and the little panel here so that you can take the front cover off. And what you have inside is a power supply. This black module here is a power supply. And then here is the main microprocessor board and the digital readout. And of course the switches to control what you want to do with your charger or discharger. So I ran it like this to see what was really going on originally. And what I found was this black case, it's plastic, was getting fire hot. Now my unit was still working, it was still doing the readouts, there was nothing wrong as far as charging and discharging cells. It's just that this thing was fire hot. And it smelled like it was so hot that it was ready to burn and melt. So looking at this little module, I see that it's totally sealed. It's a black case, plastic ultrasonic welded case, and there's absolutely no ventilation. So then I've already taken the side off of this one so that you can see it. So when you look inside it, you see that there is two little heat sink pieces of metal. This large piece of metal is acting as a heat sink, and this is acting as a heat sink for the other semiconductor. Could be MOSFETs or it could be transistors. I didn't look. It doesn't matter for this situation. The point is these things get hot, but this whole thing is in a plastic case, so there's no ventilation. When you first run this, until the heatsink gets to the same temperature of the transistor or the MOSFET, the heatsink does its job. But once they're both at the same temperature, then where's the heat to go? It can't get out of this trapped air box through plastic. So So one part of my solution is to remove that case, remove that half of the case, and leave it open and just let it sit like this. So you would think, well, now that works. Well, no, it doesn't work, because when I powered it back up and started doing some testing with the batteries again, I found that these heat sinks right here, they still get pretty hot, and far hotter, I think, than they ought to be for these switching FETs or transistors, whichever they are. Most likely they're MOSFETs. So that by itself is not a good enough solution. It's better than nothing, but it's better than having that plastic case around it, but it still doesn't really solve. The real thing is we shouldn't have a temperature above whatever the ambient temperature in the room is. The other thing is, looking down right here at this lower right hand corner of the board, there are two resistors. These are precision resistors, and these two resistors are used in the charge and discharge function when you hook a cell up to this, and then the little processor does its calculation. So if these resistors change value, it'll throw off your calculation. And also, resistors aren't meant to stay hot permanently. So if you allow these to continually get hot, even if, let's say these resistors are rated at 5 watts. If you continue to let them stay hot at 5 watts, their lifetime is going to be low. So, and as their lifetime ages, their resistance value changes, and that's going to throw off your calculation. So over time, if you allow these things to get hot and get cold and get hot and get cold in a normal cycling of your unit, you're going to end up having to throw away this whole thing because of the heat problems. So now we have not only a power supply that's got heat issues, we've got these power resistors that have heat issues. The rule of any electronics, no matter of what century or even the future centuries, it's going to always be true. Heat is not a friend of electronics. You want to keep heat away from electronics. And if you have heat, there's either one of two things going on. Either you wanted heat and you designed it, so you made like an electric stove oven, so you designed it to be hot, or you designed something and it's getting hot and it's not meant to get hot, but it does get hot, so that means there's an inefficiency, and that means that was a poor design. Or it's getting hot because there's a problem that is developed, such as in this case, it's a combination of a poor design and aging effects, which I'll get into in just a moment. So the first problem I had with this is, like I said, it was the power supply. So how I solved that is, give me just a moment to move stuff around. So how I solved that, just for the proof of this being a solution, is I simply got a 12-volt computer fan. Let me see if I can get that closer. Nope, that's as far as I can go. Right, so I got a computer fan, and I've got it so that I can adjust it to where I want it. So this fan looks too big for this, but it actually turned out to be pretty good because it doesn't have that high shrill screaming effect, that noise effect like a small fan. So I like this larger fan because it's quieter. Anyway, it's simply a 12-volt fan, and I simply took a power supply. Right here you can see it's just a little small power supply that I just simply plug in the wall to run the fan. So when you plug in the power to the iMax, I just simply also plug in the power to my little fan. So the fan's already going as you turn this on, and before you program it into whatever kind of battery type you're going to use to charge or discharge. So now that this is running and spinning, for example, that's solved all of my heat issues. There's plenty of flow from this fan, and it blows downward on the switching power supply as well as on the microprocessor, and there's plenty of ventilation that's going over here to these power resistors. These are the most precision components on this board, I believe, and it behooves us to keep those things as cool as possible. So this fan being here covers it all. Now, if you want to get pretty, yes, you can put it in a glass, or you put it in a plexiglass little display box or a cage or something, but for me, I'm just simply wanting to charge batteries and get on with my power wall, so it doesn't have to look pretty for that function. And I didn't even bother to put this back on it, but a person could. If you wanted to use smaller fans, you could probably fit the fan somewhere else and run a little air pipe with a diverter to divert flow both to the power resistors and over to the heat sinks on the power supply. You could do that too. But for me, I'll just leave this off. I don't need it. This gets the most ventilation possible. Now, now when I did this after 6 months, that seemed to solve that problem. So you could touch these power resistors after charging and discharging, and you couldn't even feel them being different from room temperature. That's how good the airflow was on this. So that solved that. The next problem I encountered was about 6 months ago. I started noticing that my capacities from the same cells that I charged and discharged a number of times were being way inconsistent. For example, the first time I measured them, they were like 1500 milliamps. But then after waiting a week and then recharging them, letting them rest a day, and then discharging them and checking their capacities, it would read like 500. And for me, anything under 500 is throwaway. So I thought it was kind of strange, but after looking at a number of videos on YouTube, I saw that a lot of people are mentioning that their cells that they get out of laptops were usually from 1,000 up to 2,200 or 2,300 or whatever, but few of them were down in the 500s to 1,000 in terms of like 30% of your hull being bad batteries and only 60% being usable. So I thought that was kind of strange, and then I started noticing that when well, let me get the connection. So here's one of those connection adapters that I was talking about earlier that comes with the units in the box. They have the plug-in banana plugs to go in the side, and I'll just plug it in just like you would expect. So then I was taking these and charging these lithium cells just like you would expect. I'm not going to do it now because this one's fully charged. But so what I found strange was this connector that's on here. I've already snipped this one off, but just to show you, this connector on here, when I would wiggle this end, or if I wiggle this end, what I found is the milliamp capacities were changing. It was a slow change, not a quick change, but it was quite a bit changing. The time element would change as well. It would indicate that there's, well, I don't mean the time element, but the milliamp up to that point of time, it would show like that it's at 3.2 volts, which you think it's getting ready to be empty. But then when you wiggle this, you would see that it jumps up to 3.7, which is a lot more closer to charge than 3.2 is. So there was something fishy going on there. But because it was charging up the batteries, I didn't really make an issue out of it until I was reading what other capacities of other guys' YouTube videos were showing. And I said, well, I'm throwing away a third of my batteries for nothing. There must be something wrong. So that's when I knew there was something wrong. But when you measure, with your ohm meter across here, you read this is good. Even if you wiggle it, it would read good. But if you look inside here at these pins, you can see that they wiggle quite a bit. And I think what's happened is after a year of me using this to test cells, that these connections have gotten loose. So I tried taking the needle nose pliers and bending them a little bit just so they'd be a tighter fit to each other. And I still was encountering the same thing. I could wiggle one of these wires or the other ones, and I would notice that the milliamp display readout would be shifting around. And if this was a good connection, that wouldn't be happening. So then I thought, well, maybe it's these that are not making a good connection. Well, if you take the jacket, slide the jacket off, you'll see that it's a pretty lousy connection. So what I always do on these alligator clips is I always solder the wire on there and don't rely on their crimp. So I had soldered these on, but when I was still using this, you still could get that inconsistency when you check this and wiggling this around. So that means that for who knows how long, I have inconsistent readings, and I was labeling all my cells not knowing that they were not reliable readings. So now I've taken a large amount of time to start all over and recheck all of my cells. So the fast solution, because I'm in a hurry to get my power wall up, the fast solution is to cut that stupid connector off and just solder it and put heat shrink around it and be done with it. Because really you don't really need this adapter if you don't really want to. You can always re-splice this in or some other kind of connector to do the same job. But this type, I don't like this kind because of this looseness effect. So that was a major discovery, is how innocent this little connector was. And let me show you. You know, hindsight is always smarter than foresight. But in the foresight, you would think, well, you just take your ohm meter and you would just measure across here, and you would check continuity and say, oh, it's good or it's bad or whatever. You know, by taking your meter leads and putting them across like that. Well, I've realized since then, if this ever become a problem to me again, continuity is not the right way to go. You do not want to measure across it like this for continuity with your ohm meter. What do you want to do? Alright, this is the smart and the clever way to do it, but it's the right way and it'll never get you wrong. But let me just first explain why the continuity way is not reliable. When you take your meter, say this one from Harbor Freight, when you make a measurement for continuity, the continuity readout on your display is only measuring at very small currents, maybe milliamps or even less. And so in effect it's really just checking for voltage inside the electronics of your meter. It's only looking and confirming that there's continuity at these low current values. But it doesn't say anything about something that draws a lot of current. And that's the problem with this. If you've got one lithium cell and you've got it set for a discharge of 1 amp, for example, 1 amp is going through here. but your meter only says that the continuity is good at the like 1 or 2 milliamps, or whatever your meter has. Different meters will measure using a different amount of milliamp amperage. So it's basically nothing. So the proper way to do this, so that you actually measure continuity, but you're measuring at the real current value, is you put your load on the item so that you have the real current that's going to be going through your questionable connection. So let's say you got the lithium cell set up and it's plugged into one side, and then this is going to the charger or discharger. Then if you measure between the two sides of the connectors, the male and female sides, if you measure with voltage and not continuity, put your meter on volt reading at low voltage, say like for the lithium cell that's 4 volts or so, make sure that you're on a scale on your meter that will read 4 volts. Let's see, on the Harbor Freight, that's 20 volts is as low as you can go to read that. So for me, I would take the 20 volt scale for reading voltage, and you put that across your red, and then while you're discharging or charging your lithium battery, you look and see if there's any reading on your display. If it's showing anything at all, it's showing that there is a resistance drop. And it doesn't matter where it's coming from, whether it's coming from the wire or if it's coming from the male and female pin connection, which is my case was the problem. And then you would also do the same thing over here on the other 2 wires and measure to see if there's a voltage drop across them as well. Now you're reading voltage drops. You're not looking at current, but by looking at a voltage drop, you're indirectly checking what that current is doing. Because if there's no resistance here, that means you have a very good connection, and if you have resistance here, then it means you've got a not as good a connection. And sure, the wire from one end to the other end is going to have a minute amount of resistance, but if you measure across here and you know that the lithium battery is 4 volts, for example, and you measure across here and you're reading 3 volts, then that means that there's a very lousy high resistance connection, and then this thing is a suspect. There's a problem with that. And this is the way I would have done it had I known that this was the problem to begin with. But you know, in the beginning I didn't know that this. I just couldn't believe that a brand new connector could be such an issue. So that's the trick, is to measure with volts, not ohms continuity. Let me see, is there anything else I've missed? I think that's about it. Oh, the only other, one more thing, let me show you this. If you don't want to use the switch mode power supply that comes with these units, you know, of course they also have this alligator clips and a connector that you can plug into the side of here, and then you can drive the charger with a DC power source. And what I've got on my notes here is you need to have a power source of 11 to 18 volts and rated at least 50 watts. So that was another thing about this power supply, is I questioned whether or not it's safe and adequate for 50 watts. Because like I said, I was only doing single cells and it was still getting pretty hot. So I hate to imagine what it was doing if I was charging a couple of cells in parallel, for example. So an alternative to not having this switch mode power supply as a problem in the future is simply to use a DC voltage source of 11 to 18 volts, which might be your lithium power bank or a 12-volt car battery, or whatever it is that you want to use to charge with, or your solar panel and a charge controller going to this, which I've tried all those ways and it works fine. So if you did get rid of that, then that would be half of all the things that might go wrong with this unit. Let's see, what else? I know there's always something I forget to tell. Well, I think that's about it. I've spent a lot of time on this. So, hope this helps you quite a bit. Oh, now I remember. When I was originally checking this power supply module, just for reference to everyone, I was reading across the power supply to see if I had a bad power supply, because I didn't know it was a heat problem at first, although I could see it was in the plastic case. So I took a measurement at the output of the little power supply, and just for reference to everyone, I was reading 12.72 volts. And the ripple wasn't too bad. I checked the AC ripple on it. It wasn't too bad, but switch mode power supplies do tend to seem to have a higher ripple than if you were just using a regular linear power supply. But other than that, it seemed okay. But, well, I guess that was about it. So, hope this helped everyone, and onward and forward. I'm still working on the goal of being off the grid. I've finished all the solar hot water projects, and now I'm working on building the power wall. And part of building my power wall was getting this iMax reliable to check all my cells with before I make up all of the batteries in a power wall bank. So yeah, everything is coming along good now, and I hope this helps you out. And so maybe for those guys that are getting ready to bash this thing in with a hammer because they couldn't figure out why their iMax was acting flaky and crazy, it could be the heat's killing the power supply, and that's why it's acting flaky. Or, as in my case, because of these lousy these lousy connections, it's making me want to throw a hammer and smash it too. But save the money now, so since I just simply fixed it. All right, well, thanks a lot, everyone, and we'll see you again.